rundown on the exam. I forgot to write down the average for the multiple choices, though. So we ended up with about a 70 average overall. The one place that I would hope is this second multiple choice. It would have liked to have seen that one go up a little bit more above the 84%. It's better, you know, if we can get that up more like 90 or something on the second try. Both of these scores I've gone through and I essentially removed the score for problem, it was problem 24. Okay, so I think in Canvas, currently like we talked about yesterday, for multiple choice 1, it says out of 96 and it gives a little rocket ship. Multiple choice 2 still says it's out of 100, but it'll be out of 96, and I just got to figure out how to manipulate those things and not screw it up. All right, so let's see. We do have a review session tonight if you want to go, and Thomas can, you know, go over some of the exam and stuff. I will today try to get the all the keys posted and everything so you can compare and everything. All right, so any question on the exam at this point? No. All right, so we have one more reaction to cover in Chapter 7, and I kind of gave you just a little intro to that yesterday, so we'll pick up where we left off there. So we'll go through a few examples of this Diels-Alder reaction. And then we're going to start into Chapter 8. Chapter 8 is on substitution reactions. And we will spend a little bit of time, so let's just look kind of ahead here. So Chapter 9 is on what are called elimination reactions. Reactions of alkyl halides. Okay, and so substitution reactions and elimination reactions are going to be competing reactions. And so I'll spend a little bit of time to kind of show you how these fit together and where we're going with this. So we'll look at substitution reactions versus elimination, and then Chapter 10 is kind of like substitution and elimination reactions of some other functional groups, primarily alcohols. And so these three chapters kind of all fit together. All right. So, I forgot my clicker today as I was rushing to make it all up and get it ready, but I didn't grab my thumb drive. So I had to kind of recopy this in. So the Diels-Alder reaction is kind of an interesting reaction that it goes from a diene, reaction of a diene, just like we were talking about before, reacts with an alkene. We call this alkene because it reacts with a diene. We call it the dienophile. So that alkene just loves dienes. And when it reacts, it forms a cyclohexene ring. So it may not be really clear, you know, what's happening in this reaction. So if we try to break this up and try to look at our product and see, you know, what parts of that product could go to the diene and what parts could go to the dienophile, we see the R group, right? That clearly has to come from the dienophile. And so the way that these are broken up is that right here, this piece would come from the dienophile. And the other 4 carbons right here come from the diene. So what we see is we've got to be able to form 2 new bonds, right? We end up forming 2 new sigma bonds during this reaction. So the way that this works One thing is, remember that we talked about dienes, and remember that dienes don't easily rotate around this center bond because there's a resonance structure that has a partial double bond between there. But they can rotate, but we have two different forms of this. And so it can form into this one. Do you guys remember what we called these two conformations? Huh? No, they're not really diastereomers. They're just conformations because we're rotating around single bond, but we kind of use terms like we did before, and we just put an S out in front. So that on the one where both alkenes are pointing to the same side, we call this S-cis. And when they're pointing away from each other, we call this S-trans. Excuse me. So in order for this reaction to take place, the diene has to be able to adopt this S-cis conformation. So if we draw out, here let's do this one in a different color here too. The dienophile, if we line these up facing each other like this, we can show the reaction by pushing electrons like this. So we can see from this first step, you can think of it as an electrophilic reaction like we have before. But when that reacts with that carbon, the carbon of the alkene or the dienophile can't hold any more electrons, so this one goes over and reacts with the other end of the dienophile, and then the double bond shifts over like this. So what we get then, if we do these in the same colors, we have this part from the diene, and the double bond is shifted. And here's the portion for the dienophile like this. Okay, so the transition state for this, right, would look something like this. And we're kind of breaking this pi bond down here, so it's partially a bond. We're forming this bond here. We're breaking this pi bond here. We're forming this sigma bond there. We're breaking this pi bond, and we're forming this pi bond. All right, so in the transition state, we have electrons that are being spread all the way around this. So what is this kind of, and the way that I've pushed the electrons, what does this kind of remind you of? Benzene, right? So we've got to have this six-membered ring transition state. And these are pretty stable, and we'll see these kind of six-member transition states a number of different times. So this reaction is concerted. What does concerted mean? Yeah, everything's happening at the same time. And this is sometimes called a 4+2 cyclo addition. Okay, so 4 plus 2 indicates the number of pi electrons from each piece. Okay, so the diene over here would have 4 pi electrons, right? It has 2 double bonds. The dienophile has 2 pi electrons that are reacting, so that's where the 4 plus 2 comes from. So the one thing here is that this S-cis is required. All right, so if we had a diene that for some reason it couldn't equilibrate to the S-cis, like it was in a ring or there was some kind of tether or something that was holding it in an S-trans, then it would not be able to react in the Diels-Alder. Yeah?
When are these kind of reactions found? Just so I can, it's easier to remember
right? So they can take place whenever we have a diene and a dienophile like this together. So a diene and an alkene, separate pieces.
Is it like something in nature, or is it something?
You know, that's a good question. For a long time nobody had found any examples, but I think there are a couple of examples where researchers actually think that a natural compound could be synthesized through a Diels-Alder. You know, the other thing that, you know, you could have reactions like this where essentially it takes place in two steps, right? You do the first electrophilic step, right, to form a cation and an anion, you know, and then it closes up in a second step. But a few reasons, we'll see some examples of it for these kind of compounds maintaining certain stereochemistry and things is why that it's really shown to be concerted, so it maintains a lot of the stereochemistry. But so this is a interesting reaction to be able to build a ring and to make two sigma bonds all at once. So just for a little example here, when I was in grad school, I did a Diels-Alder reaction, and it was actually what you would call an intramolecular Diels-Alder reaction. So this is the one that I did. It had these pieces here. And then let's just say I had something like an alcohol over here. So I built up this molecule that had an alkene, you know, so the dienophile and the diene all built into one molecule. And so when I had all these in the same molecule, you just had to put it into a solvent and just heat it up to about 160 degrees. And when I did that, this reaction could cyclize like this, and it formed, actually I won't worry about, it formed two different products which both had this same ring system like this, but they differed just at the stereochemistry of these two positions. So in one of the structures, the H's on that, we call a ring junction, were trans to one another, one H going up and one down, and then the other compound, those two H's were on the same side. But in this way, you could take this acyclic compound, you know, down here, you know, no rings in it at all, and in a single step make, you know, two rings and make this kind of complicated looking structure all at once there. So there's quite a bit of application to synthesis as well for certain types of compounds. All right, so this reaction often works the best when this R group is what we could call an electron withdrawing group. All right, and so we can think about this in terms of, you know, if the first step of the reaction, even though it's concerted, if we think of the first step of this reaction as being, let me just aim it at the carbon there. Sometimes it's okay to aim it at where the bond is forming, but we could do this going to that carbon. So this looks like essentially an electrophilic reaction like all the other ones we've done. And to increase the reactivity here, if we can make this position more delta plus, then it's going to be more electrophilic and it's going to be more reactive with the diene. So the way that we can make that more electrophilic is to put some kind of an electron withdrawing group. And so electron withdrawing groups include things like, and I'll show you how they work in a minute, things like ketones or OCH3. This is called an ester. This is called a nitrile. And what else? We could also do this with a nitro group. Okay, so all of these, especially these ones that have this carbon-oxygen double bond here, it's called a carbonyl group, fit into this. And the way that it works, if we have, let's say, put our ester here, I think we looked at a system kind of like this already when we were doing resonance. Because the oxygen of the carbonyl is more electronegative, right, it tends to want to pull electron density this way, right, out on the oxygen to form a cation at the carbonyl carbon here, but then this pi bond can move that way, and so really kind of a predominant resonance structure here is like this. So by putting this electron withdrawing group here, electron withdrawing, oops, not, oh, I put my W upside down there. Electron withdrawing group here, it pulls electron density away from this position over here and increases the amount of delta plus. Okay, so that makes the dienophile more reactive. Okay, increases reactivity of the dienophile. All right. So if we're following this kind of rationale, could we place some kind of group onto the diene that would make it more reactive? What kind of a partial charge would we like onto the diene to make it more reactive? A partial negative, right? So sometimes we can see some examples where we put an electron donating group on the diene, and that's going to make the diene more reactive. Yeah, I'll show you an example like that in a minute. Kinds of variations of this reaction. So just the simple, 1,3-butadiene and ethene, aren't really very interesting examples. So let's look at this top one. So what you need to recognize in order to do a Diels-Alder, one of the kind of the keys here is if all you see is heat, the delta means heat, by the arrow, and you have a diene, okay, and this would be the dienophile, so the ester part of the dienophile is only providing resonance as an electron withdrawing group. So that part of that, this part is not going to actually, it's just going to be carried along, but it increases the reactivity. So if we want to try to figure out the product, what we have to do is rotate around here to put this diene into the S-cis conformation. Like this. And then we line the dienophile up like this. Okay, so we always want the diene aimed at the dienophile like this. And then we can just push electrons, and really it doesn't matter which direction you go, if you go clockwise or counterclockwise, but probably since this is the more delta plus end, This arrows would go to that carbon, these would go over here, these would go here. And so we would form our 6-membered ring. We'd have the 2 methyl groups over here and a double bond between them now. And over at this position, we would have the ester. Nope. So yeah, we just need to follow what these bonds are doing. So this pi bond that's over here is being used to form the sigma bond. This pi bond is moving over to form this other pi bond, and this next pi bond forms another sigma bond. So we just end up with this cyclohexene. All right? So reactions can be done, Diels-Alders can also be done where our dienophile is in a ring. So these are kind of tricky to try to draw the products. Now this is, and this, here I'm just using ethene as the dienophile. Oops. Which is a little bit harder to use in practice because it's just a gas. Okay, but again, the way we want to figure this out is we have to aim like this, the diene towards the dienophile. And so then we can draw these arrows. This goes to there, this goes to here, and this goes to here. And there's a couple of ways we could draw this. You can draw it from the top down like this, and means that this group is going to be like bridging over the top right here. Okay, so we've formed these 2 bonds right here. Another way to try to draw these is that you can draw it kind of more from the side. It would look more like this. So that CH2 group is bridging over the top. And so from this, we can see that this part right here came from the dienophile, or the diene. And this part came from the dienophile. Those kind of structures take a little practice. All right? Okay, so the dienophiles can also be alkynes. So let's see what we would get. See if you can draw, this bottom one and see what you would come up with. So the alkyne is just going to behave as the dienophile. All right, so what's the first thing we have to do? We got to make the S-cis, right? Of the diene. And then we're just going to line up this dienophile, this alkyne. And then we're just going to push those arrows around in a circle. So this can go over to here, this can go to here, and this can go over to here. So we end up with a 6-membered ring again. Double bond over here. What's different about this one compared to the other ones we've done so far? in the product. Yeah, there's going to be another double bond in the ring, right? Because the alkyne, only one of its pi bonds reacts. And so we end up with a cyclohexadiene like this. All right? Okay, I have pages of examples here that I think maybe you guys don't have. So we'll have to add these in. Okay, so this one is an example of where we have, so here, this was the nitrile. So remember, it's one of the electron withdrawing groups, and so this is the dienophile here. And here's the diene. Oops, diene. And this methoxy group can act as an electron donating group. All right, so let me see, where do I want to draw this out? So let's just draw it down here. Let's see what, so we want that into the S-cis. So how do you think a methoxy group is going to behave as an electron donating group? How does it donate electrons? Right, the lone pairs on the oxygen. Right, so it has two non-bonding pairs. And so if these, so essentially we have this atom with a pair of electrons next to a pi bond, right? So here, the resonance will be like this, with a plus on the oxygen and a minus out on this carbon. Okay, so the electron donating group, and what's going to happen in this case, so we have two different possibilities. All right, we have one possibility that, here I'm going to have to draw these all out here, which would go like this, and would be like this. Okay, so if those cyclize, then we get this product here, OCH3 here, and our nitrile over here. Okay, what's another way that these reactants could come together? Yeah, we could just flip over one of them, right? So the other possibility, let's keep the diene the same, but we angle the dienophile the other way. All right, so we just flip it over, and we bring these together. And we're going to get now the nitrile down here, and the OCH3 up here. Yeah.
Why does it react with the alkene group instead of the nitrile group?
Okay, so the question is, why does it react with the actual, so here, let me get my pointer up here. Why does this reaction take place between the alkene portion of this and not with the nitrile portion? I think in this case, because the diene is the part that has more electron density, because it has this electron donating group, that it's going to react most with the most electropositive, or the most positive portion of this dienophile. And on this case, the electron density goes this way towards the nitrogen. The nitrogen's more electronegative, right? So in this case, right, we're going to have a delta plus on this end, and so it's going to end up reacting with that most delta plus end. There are some examples where you can have other atoms like nitrogen or oxygen within the ring. But usually the ones that we're going to look at are all going to be, these other groups are all going to be just influencing the reactivity of the diene or the dienophile. So which of these two, so what's the relationship between those two molecules, the products?
Constitutional.
Yeah, they're just constitutional isomers, right? Then you could think of it as just the nitrile being at a different place. So the thing that's going to control which of these form the most is just the same simple concept that we've used over and over again, is that just minus and plus want to come together. All right, so the delta minus of one piece is going to line up with the delta plus on the other piece. So which of those two structures accomplishes that? The bottom one, right? Because we looked at this resonance structure down here, right? So we saw that the minus end of the diene was over here, right? So that's delta minus here, and the delta plus end of the dienophile is that position away from the nitrile. So in this bottom one, it's matching up the delta minus end and the delta plus end. Okay, so this one here would be the major product. Okay, so we have to, if we have different groups, if we have an electron donating group and electron withdrawing group, then we have to consider the possible resonance for each of those to figure out how the polarity lies. Where's the delta plus and where's the delta minus? And then line those up. Okay? Let me see if I have another example like that. Oh yeah, we'll do another example kind of like that in a minute. All right, so if we compare the next two, what's just the main difference of these next two? So both of these groups, this is another way to draw an ester. Okay, so the ester, the CO2 is like this, and then that has a CH3 group on it. Okay. So the main thing here is one of them is trans, and the other one is cis. All right, so they're both going to give the same type of product, but the products are just going to be stereoisomers of one another. Okay, so if we start out with the trans, then the product will be trans as well. So these groups will be trans to one another. Of course, we get both enantiomers of this as well. So this would maintain the trans. And if we start out with the dienophile being cis, then the product will be cis. Cis goes to cis. So the stereochemistry of the dienophile is maintained in the reaction. All right, everybody got that almost? All right, let's just look at two more examples. All right, so here's another one with a ring in our diene. All right, so if we put these together, let me just redraw them over here. Okay, this is called furan. And it's reacting with this dienophile. So again, we'll just push this arrows in the same way. This pi bond goes over here. This one goes over here. And this one goes here. And so we can again draw this in two different ways. One is just going to have this oxygen bridging across, ketone over here, and a double bond there. Okay, so we have in this case generated a new kind of chiral center here, right? As well, actually, as chiral centers there and there, right? So there's actually two different diastereomers that we could generate as well. So it depends on whether that ketone group on the side is going onto the same side as the bridging oxygen or on the opposite side. And so let me, I'm going to draw these down here at the bottom. So we could have, and hopefully I'll still have room for my other product one. So if this oxygen, if we draw this oxygen going up, then this group could either be up or if we keep this one up, this one could be down. All right, so what would the relationship between these two compounds be? Diastereomers, good. Okay, so let's draw these in the other way so we can see how to do this. So these would be, if we do this same kind of drawing, gap there, here's the oxygen up and bridging. All right, so in this case, this H is going down and the ketone is going up on the same side as the bridging oxygen. Whereas in this one, the ketone is going on the opposite side as the oxygen. Okay? So what we usually call these, so what we do is we look at, if we have two of these rings here, we look at the bigger one, has more carbons in it, and then we look at this group over here. And so we could say that this one is pointing down and this one is pointing up. And so this is called the exo product. Exo means kind of outside or away from one another. Over here, we have the bigger side pointing down and this ketone pointing down, and this is called the endo product. All right? And so these are not equally favored. And so what happens is that, okay, I didn't draw that one, is that, well, it's the endo product which is favored. No, what happens, and it's kind of hard to draw, what happens is that the, when these come together, let's see if I can draw this. Here, let me do it on a new slide. These other two, and we'll just finish this up. We'll do start the substitution reactions next time. All right, so let's just see if we can figure this one out without even, we don't worry about the stereochemistry so much here, but let's just figure out, we again, though, have two different constitutional isomers that could form, right? So if we could form, my pen just fell apart. Oops. Okay, here's this portion. So we could form this one. So the CN is a nitrile, like this. Or, I can make that too big. Or this. Right, so the nitrile could be in either of those two positions. So which one do you think is going to be favored? Second one? So how do we tell? What would we need to do? Right, we'd have to figure out partial pluses and partial minuses. So on the dienophile, we already know, right? We've done this one before, so the delta plus is on this end. So this oxygen, like before, can be an electron donating group. So if it is the electron donating group, which end of the diene is it going to push the electrons to? The left hand, you're right. So these are going to push here, right? And so we could get a minus charge at the adjacent position, but if we push these electrons over here and all the way over here, we see that this has a resonance structure that would look like minus here and plus over here. So here's the minus is out on the side away from the oxygen. All right, and so that minus, so this delta minus here should match up with the delta plus over here. So which one is that going to give us? The first one, right? All right, let's do this last one. Let's try to do this one backwards. What did I have on the last slide? So you can do these backwards just by pushing the electrons around in a circle as well, right? So we could do either way. So let's say that these electrons go here. These electrons go over here. And these electrons go over here. So we're just going to kind of reverse this whole process. So we end up with a diene like this, and the way I have it drawn there would be like this, and then our dienophile would be like this. Right, so here's the dienophile, and here's the diene. And this is one that, notice that this ring of the dienophile is pointing down towards this side that has the double bond. So this would be the endo product. Okay, the exo would have this ring pointing up where these hydrogens are going. Okay, so because we have the double bond side here pointing down on the same side, so these are kind of pinched down together. So that's called the endo. All right, so I got one more slide here. I don't know what it is. Everybody got that thing copied down? All right, so we had, in this case, oops. Blue. So here's our diene, and the possibilities are that the endo one that I said would fit formed if this ketone is down underneath the diene. Okay, so the two possibilities are like that, or having this diene like this with the ketone over this way. Right? So what we're doing is we're forming bonds between from here to here and from here to here. Right? Or here, oops, not to there. From here to here, from here to here. Right? So this one would give endo, because this ketone is pointing down away from the oxygen, and this one would give exo. So the reason the endo is favored is because, remember, to have these pi bonds, these have all these p orbitals here, right? And this ketone also has a pi bond. So what happens is that the pi bond for the electron withdrawing group and the pi bonds in the diene, they can kind of stack on top of each other. And they create an interaction which is more favorable than if that ketone is pointing away. Okay, so the pi bonds stack. It's called a secondary orbital interaction. Okay, and that can only happen in the transition state going to the endo product. So we always see that side chain pointing down towards where the new alkene is formed. So it's not so much of a steric thing, but of an electronic interaction.
So by stacking, what do you mean? Like that they lay on top of each other?
Yeah, they kind of lay on top of each other. It's kind of hard to draw. Oh, that was the one we already talked about. That was my extra slide. All right, so tomorrow we will start into Chapter 8, into the substitution reactions.